This is George Easton at the Graduate School of Business at the University of Chicago. The purpose of this videotape is to present a new dynamic graphical diagnostic method that works with almost any model. In this tape, I will present the idea only with multiple linear regression, but extension to other models and fitting procedures is straightforward. The motivation for the idea is based on sort of looking at regression diagnostics backward and combining this with a visual version of the 2-factorial experimental designs that are used in response surface analysis. This results in a graphical controller which is easy and intuitive to use. First, let's consider the usual linear regression model. In the usual linear regression model, we think of y sub I as being a linear function of some x's plus a true error drawn from an unknown distribution. That is, y sub I is equal to alpha plus beta 1 x sub I1 plus beta 2 x sub I2 and so forth, plus epsilon sub I, where epsilon sub I is the draw from the unknown distribution. When we fit a line to this data using a linear regression fit, we end up with y sub I is equal to alpha hat plus beta hat x sub I1 plus beta 2 hat x sub I2 and so forth, plus a residual e sub I. That is, we have decomposed the data into y sub I equals y hat sub I plus e sub I, or the data is equal to the fit plus the residuals. There's nothing different about the model that I have written up here from the usual linear regression situation, except that I have not specified the true distribution of the errors and have not specified the fitting procedure. In what follows, you can think of these fitted coefficients, alpha hat, beta hat 1, and so forth, as being least squares regression coefficients, but it really doesn't matter what fitting procedure was used to obtain them. In regression diagnostics, many plots of the residuals are often considered, but the most important ones are the residuals versus the fitted values, the residuals versus each of the x's, sequence plots of the residuals, and normal quantile plots of the residuals. Sometimes other plots are considered, such as added variable plots, but for the method I present here, we will only consider these residual plots. To motivate the dynamic graphical diagnostic method, first consider the so-called leave one out regression diagnostics df beta and df fit. The idea behind df beta is to examine what happens to the fitted coefficients when the ith observation is omitted. df fit is similar, except instead of looking at the regression coefficients, we look instead at the fitted values and look at what happens to the ith fitted value when we omit the ith observation. Other procedures have been proposed based on changing the ith observation instead of omitting it, or looking directly at the derivative when the ith observation is moved. The leave one out regression diagnostics are very appealing because it's very natural to think that some of the observations might be bad. In this case, the beta hats that are obtained omitting the bad observations ought to be better. One way to think about the leave one out regression diagnostics is they give you a set of beta hats to consider that should contain some better ones than the beta hat obtained using least squares regression. One criticism of the leave one out regression diagnostics is that they are unlikely to detect bad sets of data when 2 or 3 observations really should be omitted. The reason, of course, is that only one observation is being omitted at a time. You can view the regression diagnostics sort of turning them around. Instead of omitting or moving the data points, what you're really trying to do is move the beta hats. In this case, we can think about procedures for moving the beta hats directly, and instead of looking at how changing the data affects the beta hats, we change the beta hats and look at how this affects the residuals. Now, the motivation that I use for developing a mechanism for thinking about manipulating beta hat directly comes from response surface analysis. If we think of our diagnostic plots as a function, a nonlinear function, their goodness in a sense, as a nonlinear function of the regression coefficients, then we can appeal directly to response surface analysis. In response surface analysis, we would consider a 2 to the p factorial design around the fitted coefficient beta hat and look at the function of interest, which in this case is how the plots appear to us, at each of those points. In response surface analysis, the set of beta hats we would consider would all be based on the beta hat given by the original fit. So the beta hat in this case is beta hat 1, beta hat 2, and so forth up to beta hat p, the p-dimensional vector. We'd consider changing this p-dimensional point by adding and subtracting a delta from each of the coefficients. It wouldn't have to be the same delta for each of the coefficients, but this, of course, gives a 2 to the p factorial design. I'll describe a little bit later how delta can be selected for each of the beta hats. But first, I want to show you a model of this situation in 3 dimensions. I've drawn here on this piece of paper an x and a y-axis. But we're thinking about a 3-dimensional model. So imagine a z-axis coming vertically out of the desktop. This model is intended to represent the 2 to the 3 factorial response surface design. The red cube in the center represents the original beta hat from the original fitting procedure, such as least squares regression. The corners of the cube represent the points in the 2 to the 3 factorial design. There are 8 corners to the cube. For example, the corner in the back here represents beta hat minus delta for each of the 3 coefficients. The corner in the front here represents beta hat plus delta for the x coordinate, and then low values for the y and the z coordinate, and so forth. So one way we could think about doing the graphical diagnostics is to calculate the residuals for the fit given by the original least squares coefficient, and then the fit for the beta, the residuals for the beta given by each of the corners of the 2 factorial design. We want to develop a dynamic graphical method. So what we need to do as a next step is to take this idea and see if we can't find, instead of a 9-plot static method, a reasonable dynamic method based on this idea. I'm now going to show the next model. This model also represents the 2 to the 3 factorial design. In order to develop a dynamic graphical method, instead of just looking at the 9 static plots given for the original beta hat plus all of the beta hats for the points in the 2 to the 3 factorial design, we can think about developing a method of moving continuously between the points of the design. In fact, one path we might use is as follows. If we start in the back, which corresponds to minus, 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 so this is beta hat 1 minus its delta, beta hat 2 minus its delta, and so forth. All 3 beta hats take their low values. We could then move along this edge to this front edge, front corner, and this corresponds to beta 1 hat taking on the high value. So it's beta 1 hat plus delta, but the other 2 betas are low. We can then move along the front. At this corner, both beta hat 1 and beta hat 2 take their high values. Beta hat 3 is still taking its low value. If we move back along the edge to the back, we have beta hat 1 taking the low value, beta hat 2 taking a high value, beta hat 3 taking the low value. When we move up to the top of the cube, beta hat 3 then moves up to its high value, and we can just move back through the sequence on the top half of the cube. When we get back to this corner, we can complete the loop by just moving down to the corner that we started with. Okay, so what we have is a continuous path that goes through all of the vertices of the cube. And we can think about a dynamic graphical procedure based on moving beta hat through all of these vertices along the path that I've painted here in red along the edges, and watching the residual plots as we do that. That path can be easily represented on the screen as a 2-dimensional object. There were 8 segments in that path, and we can represent those as an octagon in the plane. So the dynamic graphical procedure would work by moving a mouse or a cursor along the edges of the octagon in the plane. And the point that the cursor is at corresponds to a point on the edge of the cube that I was showing you, which gives a beta hat, and from that beta hat we calculate residuals and so forth. So the edge of this octagon can represent a controller in the plane corresponding to the edges of the cube. Each vertex of the octagon corresponds to one of the points in the original 2 to the 3 factorial design. Notice that this controller really gives you the notion of moving around in much the same way that we're really trying to move around the original beta hat. You'll notice, however, that there's an additional dimension to this controller. It's a two-dimensional, the surface is two-dimensional, even though the edge of the controller is only one-dimensional. So we can think about using the interior of the octagon to control another dimension of the exploratory technique, and that can be done as follows. We can think about using the distance away from the center of the octagon to interpolate between the original beta hat in the center and the edge. So if we move around the edge of the octagon, we move around the path as before. But as we move towards the center of the octagon, we move up towards beta hat. So if we were to put our cursor directly in the middle, we'd be directly on beta hat. Now the third model will show all of the planes, all of the places that beta hat can be. This model shows the beta hats that we can obtain using that idea. For example, if you move along the first edge, you move along the edge of the cube as before, down here. But if you're allowed to interpolate anywhere between that edge and beta hat, you can move beta hat to any point on this triangular surface. In a similar fashion, as you move beta hat along the front edge, when you interpolate to the original beta hat in the center, you can move your controller beta hat anywhere through this triangular region. As you move back along the edge over here, you get a third triangular region. When you move from the bottom of the cube to the top of the cube, you get a vertical triangular region. And as you move back through the top, you end up with triangular regions that are sloping down from the top edges to the beta hat. What you can see is that this set of two-dimensional surfaces really covers a great deal of the three-dimensional cube. You are missing a few things. You can't ever move along this edge here painted in silver because it wasn't on the original closed path through the vertices. Let me show you what a controller for these surfaces looks like in 2 dimensions. Once again, it's based on the octagonal controller. As you move around the edge of the octagon, you're moving along the edges of that closed path. The points represent corners of the cube. The middle represents beta hat. Now when you move from the edge towards beta hat, you're interpolating between beta hat and the edge of the cube. And this gives you triangular regions in the controller which correspond to the triangular regions in the three-dimensional cube. So you can move a mouse through this pie-shaped controller and be controlling location of beta hat anywhere on the surfaces in the model. As you do this, you're going to dynamically plot the residual plots and other diagnostics. It's easy to see how this idea can be generalized to more than 3 dimensions. For higher dimensional problems, you will end up with a polygon with more than 8 edges. The triangular-shaped regions will continue, however, to represent interpolations between the edge of the polygon and the beta hat in the center. We're now going to look at an implementation of this idea on the computer. The demonstration of the dynamic graphical method will be run on a Sun Spark Station 1 using X Windows as the graphics interface. To get the data set up, I will use S, but the graphical method has been implemented entirely in C using X Windows. Let's get our data set up. The data we're going to look at is the Daniel and Wood stack loss data. It's stored in S, so I'm going to run S+. The data set consists of 21 observations. The first column is the stack loss, the Y variable. The second column is the airflow, which is the first X variable. The third column is the cooling water temperature, which is the second x variable. And finally, the fourth column is the third x variable, which is the acid concentration. I've created a small file which contains the commands necessary to run the program. So let's look quickly at that. In this file, the first line sets up the design matrix X as just columns 2 through 4 of the data set we just looked at. The Y variable is the first column. The next line removes the means from the design matrix so that it's recentered. After that, we do a least squares regression fit, save the coefficients and the standard deviations of those coefficients. And finally, this command, regx, writes out the files necessary to run the dynamic graphics program. In regression, I've called this program Regression Explorer, which is what regx stands for. The next file we need to look at controls the layout of the screen. The layout of the screen will be an array of 2x4 windows. The lines that say plot 1, 1, 1, 2, and so forth control which plot will be in each of those windows. So the very first plot is a scatter plot of the residuals versus the first x. The second plot on the top row is the residuals versus the second x, and so forth. Finally, the fourth top plot on the top row is the residuals versus the fitted values. On the second row, we have a sequence plot of the residuals and then a QQ plot of the residuals. I'm now going to run the program. Here's the layout of the screen for the Daniel and Wood data. The upper left-hand plot are the residuals versus the first x. And as we move from left to right, we get the residuals versus the second x, the third x, and finally the residuals versus the fitted values. On the lower row, we start with a sequence plot of the residuals, a QQ plot of the residuals, and finally, on the left side, the controller. For the purposes of the video, I'm going to run the program with a smaller number of windows so that it appears larger on the screen. But I wanted to demonstrate how the screen might look if you were working on a real problem. Here's the larger screen. I've reduced the number of plots to 4. In the upper left-hand side are the residuals versus the first x, then the residuals versus the fitted values. On the lower left side is a QQ plot of the residuals, and finally the controller. Let me demonstrate the features of the program. First, I control the location of the cursor in the controller by pushing down on the first mouse button and moving the cursor. And as I do this, you can see the points move. Immediately to the right of the controller is a window which indicates the location of the coefficients. If I'm at the original least squares fit, the cursors in this window are all in the center. As I move the cursor away, the cursors in the window to the right indicate the current values of beta hat. So I can see as I move away from the least squares fit, if I move horizontally along this line, all of the coefficients go to their low values. As I move around the edge of the controller, the coefficients move one by one. First, coefficient 3 moves up to its high value, then coefficient 2 moves up to its high value, and then 3 moves back down, and so forth. Tracing out the path through all of the vertices of the 2 factorial design. The numbers along the edges of the controller indicate the coefficient that is moving as the cursor traverses that segment. So, for example, we're moving coefficient 3. There are other features of the program. We can brush the residual plots. For example, if I brush this clump of points in the residuals versus fitted values, I can see the corresponding points in the residuals versus x1 and also the QQ plot of the residuals. In addition, I can identify points. This, for example, is observation number 4. It's highlighted in the other two screens and identified in the title of the plot. Observation 4, observation 3, and so forth. Let's start exploring around the original least squares fit. We're looking for residual plots and QQ plots and so forth that are, in a sense, interesting. The original least squares fit. The fit to the data that Daniel and Wood obtained after a fair bit of analysis was the fit they got with least squares when the observations 1, 3, 4, and 21 are deleted as outliers. There's observation 21, observation 4, observation 3, and observation 1. That fit is essentially the following fit. Let's move back to least squares and watch what happens. As I move the cursor to the fit that Daniel and Wood found, the main body of the data here will rotate essentially to horizontal, also in the residuals versus x1 plot. The outliers will stand out more as outliers in the QQ plot of the residuals. There's another interesting plot that we saw when we were doing the tour around the original beta hat, however. And I think it's a plot that's at least as interesting as the fit that Daniel and Wood found. What we have in this fit is the majority of the data is quite tight around a horizontal line, with, in addition to the outliers 21, 4, 3, 1, the outlier 2. Notice how this particular fit shows the clump of points. These clumps of points correspond to near replicates of x1. Let's look one more time for other interesting fits. I had mentioned earlier that in making the plots, we could ignore constant terms and only worry about the slope coefficients. So in this 3x problem, we have 3 slope coefficients and 1 constant term. The reason is that the plots are all invariant to the constant term. In other words, what we're looking for in the plots is the majority of the data lying tightly around a horizontal line, and we don't care about the location of the horizontal line. In this way, we don't have to worry about 4 parameters, but only 3. The fit that Daniel and Wood found down here is also the fit that Andrews found when he used robust regression. Daniel and Wood go on to explore fitting curvature in this model, an x squared term of x1, and we will now look at that case. We need to look at the program that will run the necessary commands to look at the case that includes the x1 squared term. In this file, the design matrix X are once again the columns 2 through 4 of the original data set. We need to add an additional column, which is x1 squared, and the second line does that. We want to only add the part of x1 squared that's orthogonal to the design matrix, because that gives us a better estimate of the variance associated with adding that term and will make the graphics more stable. So to do that, we take x1 squared and regress it on x and save the residuals. We append that to the original design matrix and then sweep out all of the column means. Y as before is just the first column of the original data. We fit the least squares regression coefficients and save the standard deviations, and then run the Regression Explorer program that sets up the files. We now have the four-dimensional case. So coefficient 1 is the coefficient on the first x, coefficient 2 on the second x, and 3 the coefficient for the third x. Coefficient 4 here is the coefficient for the x squared term. Let's just quickly explore around the least squares fit. The fit that Daniel and Wood end up with after deleting the outliers, observation 21, 1, 3, and 4, is essentially the following fit. Notice how, as I move the cursor through the variable x4, that the space curves. This is the variable, once again, that corresponds to the squared term of x1. See how there's a curved line here, and as I move the other way, it flattens out, and then finally curves in the other direction. Once again, however, there is another very interesting fit that corresponds to the one that we were looking at before. Once again, the majority of the points are tight around the line, showing a clump just above the line. One of the differences between this fit and the other fit is that the observation 2 is now distinctly an outlier. Once again, exploring around the least squares fit. Daniel and Wood also explore some models that have the log of the stack loss as the y coefficient. These models give what I think are the best fits, and we'll look at those next. Let's look at the command file that runs the example with the y variable logged. This is a three-dimensional example again. The first line sets the design matrix X to the columns 2 through 4 of the original data, and then sweeps out the column means. Y now is set to the log of the first column. We then fit a least squares regression fit and save the coefficients and the standard errors, and then run the S function which writes out the files necessary to run the dynamic graphics program. And after that file's run, we'll execute the program. Here is the least squares fit using log y. Notice that the residuals versus the fitted values don't really look all that good. They don't look like a bivariate normal. There's a clump of points distinctly visible, and also the usual outliers. There's observation 4, observation 21, observation 3, and 1. Let's look for a better fit around this least squares fit. One of the fits over here looked interesting. In this fit, the majority of the data lies horizontally and reasonably tightly around a line, both in the residuals versus fitted values and in the residuals versus x1. We still have the following outliers. Observation 21, observation 2, observation 1, and observation 4. In addition, we have a distinct clump of points. This clump of points corresponds to the clump that we saw in the fit using raw y, but that was close to the horizontal line. Notice the advantages of this procedure. We have quickly and easily found the fits that Daniel and Wood found after extensive diagnosis. In addition, we found an interesting fit that they did not find using log y. The controller allows easy exploration around the original beta hat and gives very natural and intuitive feelings about being around the beta hat, but also the distance away from the beta hat. As we've seen from the Daniel and Wood example, the dynamic graphical diagnostic method is a simple and intuitive method to explore around a regression fit. All of our examples have started with a least squares regression fit, but we could have just as well started from a robust regression fit, and that would probably give us a more interesting set of plots to observe. A couple of things before wrapping up. The deltas in the example were chosen as a constant multiple of the standard deviation of the regression coefficient from the least squares fit. In particular, we were using 3 times the standard deviation for each coefficient. So it would be 3 times the standard error for beta 1, 3 times the standard error for beta 2, and so forth. Choosing the deltas is done more or less intuitively at this point by playing with the factor that we multiply the standard deviations. The intuitive notion is that the standard deviations are giving you some idea of size, the size of the coefficients, or the variability in the coefficients, and therefore seems like a reasonable and intuitive factor to use for each of the betas. Finally, I wanted to say a few words about applying this idea to other models other than least squares. In some nonlinear problem or non-least squares problem, we apply the model or the idea in exactly the same way. What we need to have is a fitting procedure and some set of diagnostic plots that make sense from that procedure. We then start with the fit that might be obtained via maximum likelihood, for example, and we explore around the fitted parameters. We might get initial estimates of the variability for each of those parameters by using the asymptotic approximation for their standard deviations from maximum likelihood. So for example, in non-least squares problems, the betas would now be a general set of parameters, theta, gotten from a maximum likelihood fit, and the deltas would be a constant multiple of the maximum likelihood approximation to the standard errors of the thetas. This is George Easton at the Graduate School of Business at the University of Chicago. Thank you.